Hello. I see that a number of people in the seminar have been in seminars before, so I begin by to apologize that the first 10 minutes of my presentation will be roughly the same as the last time when we did Sparkle, because a bigger group is here for the first time, and I just want to give people a small impression of what our Triple Store and our tools are about. So what I'll do in this presentation, I'll first talk for roughly 10-15 minutes, do a PowerPoint presentation about the features of AllegroGraph, and then I'll dive into a much longer demo, probably taking about 45 minutes, the first half of which will be doing reasoning with Prolog, and the second part of the demo will be reasoning with our RDFS++ reasoner. Let me start with the presentation. So our presentation is a product called AllegroGraph. The graph part is to be taken seriously. We are a graph database, and working with RDF and RDFS and OWL is one of the applications of our graph database. But a whole other part of what people do with our database are things like social network analysis and by now even some geospatial stuff. Now, my marketing colleagues forced me to call this database a Web 3.0 database, mainly because we are in this space. We do RDF, OWL, and Sparkle. We do semantic search. We do social networking and distributed search. And we're all in this particular area with the features of our database, our Triple Store. Again, as I said, no, I haven't said that. One of the assumptions for this presentation is that you know a little bit about RDF and RDFS. Not much. I'll go through the basics, but I hope this is not the first time you look at having anything to do with RDF. Then I'll talk about how AllegroGraph deals with RDF and the triples. I'll talk about a few of the advanced features, and then I'll dive into the reasoning with Prolog and RDFS++. And then most of the time is the demos. So about RDF, it is a knowledge representation standard for the semantic web. The big dream is that in a few years' time, every scrap of information on the web will have some metadata attached to it, so that it is easier for machines to find information on the web or to combine information on the web. That will probably still take a few years before that dream comes true, but in the meantime, this RDF thing has become a standard for metadata in general. And for those in the audience that have been in computing for a long time and did some AI or cognitive science in the 60s and the 70s, they will see that this is nothing more than, that this RDF is nothing more than a way to serialize old-fashioned semantic networks. Now, what is a semantic network? Most of you will be familiar with these networks. Above the line is a very, very tiny ontology. You have things like a class description, so you have a mammal, which is a subclass of an animal, which is of type class. A mammal has normally 2 eyes, 4 legs, and something like a dog is a subclass of a mammal. And you have predicates, but predicates are objects in themselves, so even predicates have predicates. So here's the typical ontology, and then below the line you have some examples of individuals that are described by the ontology. Now the problem with computers is they can't look at these pictures, so you have to serialize these semantic networks. And this is how you serialize them. So this is the same picture you saw before. This is the identical description of the semantic network in triples. And so this is one triple, animal, type, class. And in RDF they call them subject, predicate, object. Now the problem with these short names is that if multiple people build ontologies, then sometimes multiple people will give the same thing different names. So you need a way to make these short names unique. And what the RDF people did is they added namespaces to words. So here we see the same ontology again, but this time in what they call n-triples format, where each word has a namespace. So you still see the word animal here, but now it's got this namespace in front of it. And they're still strings, and they call them literals. And if you want to, then you can also do this whole RDF thing in XML, but this is not something that most people ever will read. Now, how do you represent those triples in the triple store? Basically, no triple store will store the strings directly in their internal representation. What you do in triple stores is you replace every string with a unique number, and then you have dictionaries and reverse dictionaries. So again, here we see the same ontology, except here we now have the triples are represented by vectors of vectors, both in memory and on disk. And you have a dictionary that, for example, tells us that Franz animal is number 2, but also that number 2 is Franz animal. Now, you want to get information as quickly as possible out of a triple store, so from disk into memory. So you have indices on triples, and usually you have 3 to 6 indices for your triple store. So, for example, one way to index your triples is for subject, predicate, object. And so if you say, if you want to say, give me every triple with Jans as the subject, then you will use this index, and you will need one run over a cursor to find all the triples that start with Jans. If you want to get all the triples where Jans is, then you use the same index. If you don't know what the subject is, and you want to say, find all the people that are a psychologist, then you will use this particular index, and on and on. And now I've simplified my representation of the triples a little bit. Actually, AllegroGraph is a quad store. We support named graphs, and so we have 3 additional indices where the graph is the first argument, but I'll get to named graphs in more detail when I do the demo. I won't talk too much about that right now. Every seminar people ask me, what is the difference between a triple store and a relational database? So in order to avoid that question at the end, I'll handle it straight away. This is an example of a person from, this is an example of a part of the demo that I will show you later. We created a little family tree for the Kennedy family, and this is one person in the Kennedy family. So these are, looks a little bit like n-triples, but we used a shorter format where we say there's a person 2, there's of type person, her name is Rose Elizabeth Fitzgerald, no suffix, she went to the Sacred Heart Convent for a school, she was 105 years old when she died, she was a female, she got a bunch of children, and her profession was a homemaker. Now, this is a very flat representation of a person. If you would do the same thing in a relational database, you would need this table. You would need a table for a person, but then you might have multiple spouses in your life, so you need a link table to link to multiple people. You might have gone to multiple schools, so you need a link table for schools. You might have multiple professions in your life, so you have a link table for that, and you might have multiple children, so again a link table. So all in all, the representation is for a relational database is much more formal and slightly more complex. So if you summarize with a graph database, you can, with an RDF triple store, you can add predicates without changing any schema. Now, the good thing about that is that you are incredibly flexible. You can just add predicates whenever you want. The downside, of course, is that it's really, really easy to shoot yourself in the foot, because if you make a mistake with naming of the predicate, or you forget about the predicate, and before you know, you get big chaos. So one thing that people do to keep that chaos in rein is to have ontologies, but again, we'll talk about that later. Another advantage of a graph database is that one-to-many relations are directly encoded without the indirection of tables, like you would have in a relational database. So I always say that with triple store, you do most of the joins at load time instead of at retrieval time. And then you never think about what to index because all the indexes are already, all the predicates are already indexed. And again, I'll give you examples of that later. So what is AllegroGraph in general? It's a scalable persistent triple store. Right now we can read 1.1 billion triples in 23 hours on a $5,000 multiprocessor machine. The example that we use here is the Lubum 8000. We load roughly 20 to 40,000 triples per second, and we get record query performance on the Lubum benchmark. Maybe some people in the audience won't know about this benchmark. Lubum stands for Lehigh University benchmark, and it's an ontology of things in a university. So you have types of people, employees, professors, students, assistant professors, etc. Types of papers, types of organizations. And there's a generator to generate as many universities and as many apartments and students as you want. And then there's a set of example queries that you can do on that data. And if you go to our website, you can find the performance of our database with respect to that benchmark. We're totally standards-based, so we do RDF, RDFS, OWL, Sparkle, and named graphs. You can work in standalone mode if you do heavy analytics, or you can use it as an interactive database, and we have a client-server configuration. We're accessible from any language. We've spent most time so far on making sure that we run with Java. So we adhere to the Sesame interfaces, and we have a basic Java interface. But we also have an HTTP client interface, so that people using .NET, Python, Ruby, Lisp, or whatever can now use it through a REST interface. Then we have several reasoning mechanisms. We have Prolog and RDFS, the things that I'll focus on this morning. We have a description logic called Eraser, which is provided by a partner of us, and in the fall we'll present a seminar on how to reason with Eraser with a graph. And then we work with one of our partners is Top Quadrant with the product Top Rate Composer, and next Monday we'll actually have a seminar on how to use AllegroGraph with the Top Rate Composer. We have some unique features. One of them is a direct reification. So I can, in our case, our triples can point directly to other triples. Every triple has a unique ID. So say I create a triple, Steve is a man. We say that would be triple 1. Then I could have a second triple that says no one believes triple 1. Yeah, which is a really, really very fast way of doing verification. It saves you a lot of triples. We support named graphs. So triples have a fourth argument, which most people use to cluster triples. So say you have several ontologies that you all want to load in one store. Then just for versioning support, you could give every ontology its own named graph, say the file of the name, or the name of the ontology. And then say you make modifications to your RDF file for your ontology, say for example with Top Rate Composer or Protege. And what you do is you can delete all the triples that came from the old ontology and reload the new one. And so it's an easy clustering mechanism. And actually, we right now just finished an ontology versioning tool that is based on CPS. But what we also can do with this named graph is we can put trust factors in there, any type of number. And again, in the demo, I'll show you a little bit about that. We have native data types and range queries. Normally, in triple stores, every object of a triple is stored in a dictionary as a string. So if you want to say, give me every person between, say, 75 and 80, you have to go through all the triples with the predicate age, look at the string, read the string into a number, and then do the comparison. In our system, we completely integrated numbers in the triples. So we can do straight range queries, and we have to do only one cursor run to find all the ages between 75 and 80. Then we have currently we also provide some basic geospatial and temporal primitives, and we're working on making them as competitive as dedicated geospatial stores. We have a social network analysis library. It's not yet for customers. Internally we use it, and in the fall I also will give a seminar about how to do geospatial, geotemporal reasoning, and social network analysis with our triple store. And we can all combine it with Prolog and Sparkle. This is a little picture of, well, let me just go to these. Maybe this is an interesting one. So we run on every platform, which is not entirely true. Currently we run on all little endian platforms, and we're working on big endian platforms. On top of that we have a compiler. Then our graph database is just a collection of dictionaries, indices, and caches. And on top of that we have a simple API to store, get, and read files. Store triples, get triples, and read files. On top of that we have a reasoner for RDFS++ and Razor. And on top we have Sparkle, RDFS, Prolog, and Lisp. And you can reach all of this good stuff through a server interface or through other types of interfaces like Java and .NET. Let me continue. So, okay, so I basically went through my presentation about what AllegroGraph is. First I will talk about Prolog. And Allegro Common Lisp contains a full industrial strength Prolog, which is really competitive with the commercial ones. And we made a connection with the triple store, so now we can do full Prolog on a persistent triple store. And let me just dive into the first demo instead of going through a PowerPoint presentation of Prolog. Let me just dive into the demo. Any questions so far? By the way, I'm going a bit quick. Press the 6 if you want to ask a question. Okay. I will first spend 2 or 3 minutes on showing how to get triples in and out of the triple store, and then I will go talk about Prolog, and after I'm done with Prolog I will show how you can do the same thing, not in Lisp but in Java, just to give you a feeling about that it's just as easy to do this in Java as in Lisp, except if you do interactive demos this is slightly easier. So I load the triple store. So what I have here is Emacs. On the left hand side I have one buffer that contains the whole tutorial file. On the right hand side I have the listener. For people who never saw Lisp before, yeah, if you type something in you get results back, so +1 or 1, or if I do defun b minus ab. So now I define the function, done 10.4. Yeah, it's a scripting language, but it's also a compiled scripting language. Compile them, so I can do the same thing, except now it's machine code. Yeah, so it's a compiled scripting language for those who never worked with Lisp. But anyway, let's go to the demo. Now, for people who are afterwards interested in playing with this themselves, if you do this in Emacs, we also have a little script so that if you run through all the examples, you just press a button, in my case it's F8, and what will happen, it will copy the thing at the cursor to the right into the Lisp listener and will execute it and will jump back to your editor buffer. So right now I'm opening a triple store. Jumping a little bit ahead of myself. Like Java, we have packages, so I have to be in the package triple store user. And now I can open a triple store, so now I have a triple store open. I don't want to type long names, so I register the namespace O to stand for this URI. So let me do this. And now if I type something like Jans, I get back a fully expanded URI. So now let me add some triples to the triple store. Not surprisingly, it's called add triple. So add the triple that person 1 is the first name Steve, is an organizer and 52 years old. So now I have 3 triples. And there's a person 2 with the first name Jans, psychologist, and he's 48. And now the triples are in the triple store, and they're actually on disk. And you want to get them back. So you say, give me all the list of all the triples, and you get back person 1, first name Steve, person 1, age 52, person 2, let me say do list for every element in the last expression, print E, so slightly better readable. Now you see this thing default graph, don't worry about it, we'll talk about it later. This is the named graph argument. I can say, give me all the triples where the predicate, so I can get selectively triples back from the B trees from the on disk. So here I say, give me all the triples where the predicate is first name and where the object is Steve, and I get 1 triple back. I can look at 1 triple. So here I say, set the triple to the first element of all the triples that I get back. So now I have a triple. I can type triple, there's a triple. The triple has a subject of the triple. There's a predicate of the triple. There's an object of the triple. There's the graph of the triple, in this case just the default graph. And there's even, I think, a triple ID of the triple, which is triple number 1. Yeah, so it's just a structure. And in Java it's accessible in the same way. Now let me delete triples. So now I delete all the triples where the subject is person 2. And if I now look at all the triples, I only get back 3 triples for Steve. And I close the triple store. So these are really the basics of working with the triple store. And just to give you an idea how you do this in Java, simple Java. In Java, you well, this is the thing to get Java to load the jar file. Import Conforms AllegroGraph. You start a connection this way, so you create a new AllegroGraph connection. Now you open only a connection to a server. You're not yet talking to a triple store, to one particular triple store. So say you want to do AllegroGraph example 1 in the directory AllegroGraph, and then you start a new triple store with this call. Basically renew means whatever already exists, delete it and start a new triple store. Then you saw in list the add triples, where in Java is add statements, so you have triple step 1, predicate 1, object 1, and subject 1, predicate 2, object 2. I won't go into much detail here. You can add multiple triples at the same time. And if you want to get them out, you create a cursor, or we created the wildcard with just the null string. And then I create a cursor, and then I can run through the cursor and I can print triples in Java. So this is the very, very basics of the triple store. Oops. Any questions so far? Please press the 6 if you have a question. Okay. So now we go to a slightly more interesting example, and we will dive into Prolog. So let me open the example that we're going to work for the rest of this seminar. This is an n-triple file. So there's a person 1 who is of type person. First name Joseph Patrick Kennedy, went to Harvard, born 88, died in 1969, and was a male, and then has a spouse, and then a bunch of children, etc., etc. And there's even stuff about places where people were born died, etc., etc. So this is the basic triple store, and it's not a really big one. It's probably 1,300 triples, but it's a good one to do to show how things work. It doesn't matter. I don't want to do this. So here I define a function on the left to create a triple store. I call it seminar. Then I load the triples, load n triples from the file kennedy.n triples, and then we index all the triples. So I define the function, and then I run the function, and it took 60 milliseconds to load the triple store. And then, just to make sure that I have any data in this database, I say, give me all the triples where the object is male, and element star. So here are all the males. So now we have the data loaded. So let's look at the, oh, I might have loaded it 2 times, actually. Oh no, it's okay. Well, anyway, we'll find that quick enough. No, just to be sure. Close triple store. Let me load it again. Okay, there. Yeah, okay. Okay, let's go into Prolog. Some people are scared if they, for the first time, think they have to work with Prolog, but actually, if you take any Prolog book, if you look at the Prolog that we use in our triple store, it's probably only 5% of all the features that Prolog has, at least when you work with the triple store. Basically, we use the backtracking mechanisms and we use the unification mechanisms. But just let's see how to work with the Prolog. Here we have a statement called select every x where q, and q is the functor, that is the relation between Prolog and the triple store. So select every x where x has the sex male. So we execute that, and then we get a bunch of people back. Here we get all the x's back that satisfy the predicate that they are male. Now, because looking at things like person 1 and 2 is not very helpful, I created a little function that will concatenate some strings together. Don't worry about this function. And then we create our first Prolog rule. Now, this one is a little bit more complex than the ones come later, but I need this rule, so I define it now. So here I say an x. So this thing means add a rule. And if you use 2 dashes, you're actually saying forget everything you ever knew about full name and just start a new relationship with full name. So what you say here is x has the full name, if in the triple store x has the first name, and x has the middle initial mn, and x has the last name, and full name is the concatenation of first name, middle name, and last name. So we execute this one. And now I can say, select every first name where x has the sex male and where the full name of x is full name. So I do that. And then I get all the full names of all the males in my little database here on the right hand side. So now I've shown you how to use select to print things in the database using Prolog. So now let's build a little ontology about a family, not using OWL, but just using Prolog rules. One of the lowest layer rules is you need something to describe what is a male. Well, that's a very simple rule. You say x is a male if x has the sex male. So we've done that. So now we have the Prolog rule male. And again, if you want to use it, it looks a lot like the one above. We say select every x in full name if x is male and the full name of x is full name. And we get here that see. Person 57. Oops. Is Mark Cuomo. Let me do this. It's probably slightly better. So now you can see the full list. So we've done the male. So I can define female the same way, not surprisingly. Then once I've done male and female, I can define a father. So I say X is the father of Y if X is a male and X is a child of Y. Or I can say X is the mother of Y if X is a female and X is a child of Y. And once I've done father-mother, I can very easily express parents. So I can say parent XY if you're the father of someone, or parent XY if X is the mother of Y. So now note that parent has two dashes here, and this one only has one dash. This one 2, this one 1. Means that you add a rule to the parent. So there's 2 rules for parent right now. So now let's use it. So now we say select every X and F where person 1 is the parent of X and the full name of X is full name. So we do this, and then we get all the children of the first Kennedy in our database. But the power of Prolog is that we also can reverse the arguments. So I can also write a query where I say find every F where X is the parent of person 7 and the full name of X is full name. So now we find all the parents. And this person has 2 parents in this database. This is the father and this is the mother. Now once you've done the parent relationship, you can do a grandparent relationship. So you say X is the grandparent of Y if X is the parent of A person Z and Z is the parent of Y. And a grandchild is of course just the reverse. And then we get to the first recursive relationship, which is ancestor. So we say X is the ancestor of Y if X is the parent of Y, or X is the ancestor of Y if X is the parent of A person C, where this person C is the ancestor of Y. And just to see how we use it, we say, okay, find every first name where person 1 is the ancestor of X and the full name of X is full name. So we saw that Robert Patrick Kennedy probably had 7 children, but if we do this, then we see that in the database there's 39 grandchildren are descendants of person 1. And if you want all the females, you say, okay, find every descendant of person 1 where X is a female, and again the full name thing. So now we get all the females. Descendant is just the reverse of ancestor. And then we get to a point where you can't express it in OWL 1.0, although in 1.1 this is probably going to be solved, or you can solve it with swirl. But in Prolog you can directly express things like aunt and uncle. And I'm not even going to explain it because it takes at least a minute to look through this rule and find it. But if you're interested, ask Steve for this file and you can play with it yourself. So I do aunt and uncles. And then we get to nephew. So the interesting part is that by now we're probably 5-6 levels deep in terms of the rules that you call in order to define a particular predicate. So nephew is built on aunt uses various other things, all on top of each other. So this is nephews. Let me see. Oh. Yeah, I want to go quickly through this because after a while it's all the same. No, let me finish with this rule, and that's about it. So this is a rule that says parent-child have same name, XY, if X is the first name, name 1, and X is the parent of Y, and Y has the first name, N1, and X is not Y. So if I do the selecting a query again, asking for all the people that have parent children that have the same name, then we get this list. So this is the basic Prolog, and I won't go into any more detail. and I'll close the triple store. Again, I'm racing through this, so I really would like to know if there's any questions so far.
Yeah, I have a question. You showed a picture of a software stack earlier where between Prolog and the triple store you had some other reasoner like RDF++, if I remember correctly. Does that mean in what you just shown us, you actually execute something at that layer?
No. The second half of this demo, so I first do the Prolog, and then the second half of this demonstration is all about the RDFS++ reasoner, and then I'll also show how you can use the RDFS++ reasoner together with Prolog.
So this directly interacts with the triple store?
Yeah.
And all the reasoning that you've shown is just unification in Prolog?
So yeah, so right now there's no reasoning. In the second half of the demo is all about reasoning with RDFS++, and then I'll show how you can do Prolog also on top of the reasoner.
Okay, thanks.
Yeah. The Prolog that we have is also aware of named graphs. So if I load a file and I say that I load the file Kennedy n triples again, and then I say the default graph is Kennedy file, so this is just a resource, then suddenly all the triples from this file will have this additional slot. Let me show how that works. So now I've loaded the triple store again, and let me look at, say, the males again. So select every, no, let's just do get triples list. Get triples. So you can now see for person 1, is of RDF type person, and there's a fourth argument now, which is Kennedy file. Yeah. So that's the name. That is the thing that clusters all these things together. So if I now go here and say I add another triple, some more triples to the same triple store, say person 1000 with the first name Arnold, and the graph argument is interactive. This is just a URI. So I add 3 more triples. Arnold, the last name is Smith, and the profession of this person is professor. So if I now say get all the triples where the object is Arnold, I get 2 back. This will be, as you will see later, Arnold Schwarzenegger, who's actually a member of the Kennedy family, and then the Arnold that I just added. So first, let me do get triples list. First to say, okay, find all the triples where the graph is interactive. And I see I get only 3 triples back. And then I can use it in the Prolog. I can say, okay, find every X where the first name is Arnold from the Kennedy file, and where the last name is last name, and where the profession is profession. So I do this. And then I find that it's Schwarzenegger was a governor, Schwarzenegger is a bodybuilder, and Schwarzenegger is an actor. If I look at interactive, so what you see here is that you have a fourth argument. I can say, find all the ones from the interactive cluster, then you see there's only a Smith that is a professor. And the fun part is I can even say, in what named graphs is Arnold defined? And I do this query, and I can find that there's an Arnold in the Kennedy file, and there's an Arnold in interactive. And if I delete all the triples from interactive, and then I try my select again, I get 0 results. So that is the name graph argument. Then range queries. In our triple store, as I told you before, we can take about 18 native data types and incorporate them directly into the triples, to the triple store in such a way that you can do very efficient range queries over them. So here is how you do it. You say set a for example, in the Kennedy file, birth year to an unsigned long, death year to an unsigned long, and the longitude gets the data type longitude and the latitude. Fill the Kennedy database again. And then I can create rules like find all the latitudes between for x between a minimum and a maximum. And don't worry too much about the syntax of this rule. Or find all the birth years between a particular time. And you can read this later if you wanted to. So let me execute these two. And then I can say in my prolog, find all the places between -100 and 100 where the birthplace is placed, where the birth year between per person, and find the people that were born between 1900 and 1930, and give me the full name of this person. And I get all the people that were born between this latitude and between 1900 and 1930. Now I will, in a few seconds, I will dive into a much longer tutorial about, or a seminar about the reasoning, but just because I have this file open, I want to show you a little bit of reasoning before we go to the full reasoning example. Say I would add one tuple to the tuple store, and this is the tuple. Has child, the predicate has child is the inverse of child of. So I add this tuple, so this is one of the OWL inverse of things. So now in the tuple store, if I say find all the children of person 1, and we use the existing predicates, we get a list of people back. If we say select X where person X is child of X, we get nothing back because child of is not defined in the database, in the data for the individuals. But if we use this functor called QS, then what we actually do is we use Prolog on top of the reasoner, and we ask the reasoner to start working. So if we use this one, then suddenly we find the parents of this particular person. Just because it's an inverse of the same with the OWL same as. So if I add the tuple that Arnold is the same as the Terminator, and then I say find all the people in the tuple store that have the first name, the Terminator, then suddenly we find back Arnold Schwarzenegger. Anyway, we'll get back on the reasoning later, but because I have the Kennedy file open, I just want to show you a little free demo. I close the database again, and then one more thing we can do with Prolog, and then it's on to reasoning. Oh, I already have the tuple store closed. Okay. We have a file that was created by Psych Corporation, which contains a lot of information about terrorists and weapon systems. And if you want to have that file, we can give that file to you. It's got roughly 220,000 triples, and I want to use that one to show how we can point directly to triples and actually have Prolog again reason about that. So I create this particular triple store, and this one has 220,000 triples, so we have to wait a few seconds to load it and index it. So it's loaded, and I register the namespace, psych, so C, I don't want to type in the long name, and then I do a query like find every A, B, X, and P where Osama bin Laden influences an agent Z, where this person Z is a friend B, where C resides in region D and where B also has been in D, and where a person A is acquainted with B, and A is the occupation airline pilot, and B is the occupation airline pilot. And B was born in a particular place, and F was born in, and a new person F was born in that place where F has a particular belief system. So execute that query, and in 7 milliseconds I get back the answer. Now just imagine that you would have to write this particular query in SQL. Okay, but that's not to the point right now. So now let's add some reification. So I write a little function called add_blair_belief, where in Prolog I say, okay, find every triple where Osama bin Laden influences an agent Z, and I don't care about the graph, but also unify the ID for that particular triple. And then in list I add a triple where Blair believes this particular ID. Actually, I have to change this. Sorry. So what I've done is I added 4 triples where Blair believes one particular triple, or a bunch of particular triples, and then in the Prolog I do basically the same query, except I now, for the first class, would say Osama bin Laden influences the agent Z. I don't care about the graph, but I want to have the triple ID, and then I can say where Blair believes this particular triple ID. And when I execute that query, I get results back because Blair is now part of it. So if I delete the triples with Blair in them again, and I would do the same query again, then suddenly there's nothing to be done. Okay, so this concludes everything having to do with Prolog. Any more questions? Again, I'm going really, really fast.
One quick question.
Okay.
All right. So when you use the QS function call, that turns on reasoning, right? Is that what you refer to as RDF? That's plus reasoning?
No. If you see the predicate QS standing for Q smart, then you see RDFS plus reasoning. But I'm now going into that section. I'm now diving into that. Okay? So in 5 minutes, I will give an answer to your query, to question. So just let me quickly go to the PowerPoint presentation. I hope we all see the PowerPoint right now. So one problem with RDF is that you can say everything you want to say, and you won't violate anything. So you can, for example, say that Mammal is a subclass of dog, and the dog is a subclass of Mammal. And in RDF, that's perfectly legal. So one of the things that people did after they created RDF is to add a little bit more semantics to RDF, and they call that RDFS. So in RDFS, you have things like core classes, so you can say if something is a resource or class or literal, and you have properties and statements. But the most important thing is this thing here, these things here. It's things can have a type, so basically RDFS introduced a type system where things have a particular type. Things can be a subclass of, or predicates or properties can be a subproperty of another property. And there's some basic core restrictions. So you can say if you have something like pet-of relationship or has-pet, if you say the domain of the has-pet relation is a human, you mean that whenever you see that someone has a pet, you also can deduce that X must be a human being. And then there's a range. I guess most people are familiar with that. Now, RDFS in itself wasn't enough for most people. They also wanted to add logic to RDF. So, and I'm now just skipping a really, really long history. Finally, we came to a thing called OWL, which is a marriage between an object-oriented type system and a well-understood description logic. And it combines greatly with the XML and RDF. And the typical things that you do with it are class membership or equivalence of classes and things like that. So it's got more semantics than RDF. So you can do existential quantification or universal quantification. You can do intersection, union, one-off. That's cardinality. And then there's things like same as, inverse of, transitive properties, symmetric properties, functional properties, and all that stuff is well described on the W3C web pages. I always give this example, and that example is, hey, if you look at this particular semantic network, would there be an answer to the query, Mr. Aßmann owns something where X has two eyes? And usually when I do it live, I give people a few minutes, but in a seminar I won't do it. Basically, you can get an answer to this query by saying that Mr. Aßmann is the same as Jans, and Robbie is a pet of Jans, so pet of is the inverse of has pet, and the range of has pet was Mammal, so yes, there is something with two eyes. That's the typical kind of a visualization of the reasoning you do with the RDFS and OWL. So we, for AllegroGraph, as I told you at the beginning of this presentation, have a full description logic, which is provided by our partner Racer, which does full OWL on top of the triple store, or on any RDF or OWL ontology. And something like Racer and Palette are complete in the sense that it will give every answer that you can derive from a particular ontology. The problem is, if you work with literally millions and millions of individuals that are described by an ontology, then suddenly it becomes very unpredictable of when you get an answer. It might take a millisecond, it might take a year before you get an answer. So we talk a lot with customers, and they wanted faster performance, and they're willing to sacrifice some of the power of OWL. And so we came up with this compromise, and actually other triple store vendors now all come to this thing that some call RDFS++ and some call OWL Lite, but it's what the name already tells what it is. It's a little bit more than RDFS++, or it's slightly less than OWL. And we have a full OWL Lite or RDF++ reasoner in AllegroGraph. So how does it work? Well, I'll demo it now. So let's look. Let's look at this function. In Java, you do the same thing. If you want to use, you've seen me use several times this thing called get triples list. And this thing will get directly triples from the triple store. If you set a variable use reasoner to true, or in Java you do get triples list with the flag for use reason is true, then suddenly the reasoner will give you not only the real triples in the triple store, but also the inferred triples in the triple store. So I need this function. This is just a demo version, a demo function. I register some namespaces like RDFS, RDF, OWL, and RDFS. And now let's go through all the predicates that we support from RDFS and OWL. And the first one is inverse of. So say I add a few triples like Jans owns Bira, where Bira was one of the cats that I had. It was roughly 10 kilos. And I add a triple owned by is the inverse of owns, and has is again the inverse of owned by. So now I can do a query where I can say, is Bira owned by nil, by someone? And if I just would do a get triples list without reasoning, I wouldn't get any results. But if I turn the reasoner on, then suddenly I do get a result. And I get a triple back that says, Bira is owned by Jans. Yes, so this is a very simple form of reasoning. Reasoning is really too much of a word in this case. I can say who owns by whom, or who is owned by Jans. So all the things that normally work, all the variations that you could do with the triples list, also will work with when the reasoner is turned on, and the inverse of inverse of will work. So we saw that owned by is the inverse of owns, and has is the inverse of owned by. So I can say Jans has something, and I will find that Jans has Bira. And I can say who has what, and all that stuff will work. Now, how does it work with the Prolog? Several of you have asked about it, but I can use this stuff straight in Prolog. So say I would do a select X, where Bira owned by X, then normally I don't get a result back. Why? Because owned by is not in the tuple store. However, if I use this little thing here, QS, in Prolog, then suddenly there will be a result. In this case, Jans. Why? Because the QS actually triggers the reasoner. So this is relatively important to understand. So anyone with questions about this part? Okay.
I have a question. This is Franz.
Hi, Lance.
Hello.
Hey, in order to, I could do most of, or maybe all of what you're doing with RDFS and Prolog.
Yeah.
It seems like I would have to establish some rules to say what is an inverse or what is a subproperty. Is that true?
Yeah.
So what's the advantage of going to the RDFS versus doing it in Prolog? Just two options to do either way?
I have a version of the reasoner which is completely written in Prolog, and it is slower than the reasoner. So the reasoner is completely optimized for doing RDFS++ reasoning. The Prolog in itself is a very, it's just doing a backtracking from top to bottom, yeah, and it doesn't know a lot of the constraints that you have for RDF and RDFS. The Lisp version that, or the Lisp version that I have is completely, totally geared to making it as efficient as possible, hashing a lot of intermediate results, like inverse of relations. I don't look every time in my database to figure out that something is the inverse of something. I have inverse of relationships, subproperties all hashed in memory, for example, in the RDFS++ reasoner. So it can be 10 to 100 times faster than an unoptimized Prolog version. I probably could optimize a Prolog version, but that would be a lot more work.
That makes sense. Thanks.
Yeah. So we do subproperty of. So if you can say, so every time when I do make tutorial store, by the way, I create a new triple store. So I say add triple Jans has pet Bira, and then I say has pet is a subproperty of owns, and then just a triple where I say Bira is a friend of Samira. And then I can say does Jans own Bira, and the answer will be a new inferred triple, which basically means yes. And why? Because has pet is a subproperty of owns. So if you has pet, then you also own it. And then all the queries will just work. And you can even combine it with select every X and Y where in the tuple store Jans owns X and X has a friend Y. Actually, I can get rid of this S here. So only the owns part is done with the reasoner, and the rest is just plain Prolog. And I can find that Bira and Samira are friends. I can do combine inverse and subproperties, and you probably will all believe that. Given the time, I will just run to same as. I make a new tuple store. I say Jans owns Bira. Jans is the same as Jannes, and Asman is the same as Jannes, and Bira is the same as son of Samira, which was another really great cat that I had. So now I can say things like, does Asman owns son of Samira? And yes, the answer is yes. although there's no straight triple, you can see that Asmund was the same as Jonas, and Jonas was the same as Jans, and Bira was the same as Samira. Sorry, Samira was the same as the son of Samira is the same as Bira. So yes, you get an answer, and it works again in every possible combination. Now you can combine same as with inverse of subproperty. All these things are completely orthogonal, and just to understand how it all works, I have this tutorial that you can get from me if you ask me for it. Then the RDFS thing is subclass, so I make another tutorial store, and I say a mammal is a subclass of animal, a human is a subclass of mammal, a man is a subclass of human, and Jans is a type of man, and Jans is the same as Jonas, and Asmund is the same as Jonas, so I combine it. And so now I can say, is Jans of type man? Well, of course, because that was a straight triple. You had the triple here. But then I can say, is Jans of type human? And yes, I also get a triple back. And the reason is because Jans is a man, and man is a subclass of human. I can say, what are the types of Jans? And I find that Jans is a man, a human, a mammal, and an animal. So it will give you the whole subclass hierarchy. And it, of course, combines again with same as. So I Asmund what all the types of Asmund, and I get the same list back, because Asmund is the same as Jonas is the same as Jans. Then I'll only show you the range, because it works the same for domain. So I create a new triple store. I say Jans has pet Bira, and has pet is the range pet, which means whenever I see that someone has a pet, then that thing also must be a mammal. So we say pet is a subclass of mammal, and fat cat is the same as Bira. So now I can say things like, is Bira of RDF type pet? And I get an answer back. Why? Because Jans has the pet Bira, and has pet as the range pet. And I can even say, is Bira of type mammal? Because as I said before, all the mechanisms are orthogonal. So I can say Bira is of RDF type mammal, because, well, I'm not going into that. And then finally, a transitivity, and then I'm done with the reasoner, and it can take questions. So I make a new triple store. I say that the contains relation is a transitive property. So now I can say things like, the USA contains California, and the Golden State contains Contra Costa, which is the country I live in, and Contra Costi contains Moraga, which is the city I live in. And then I do some things with same as. I can say, well, the USA is the same as Uncle Sam, and Moraga is the same as my town, and California is the same as Golden State. And now I can say, does the USA contain Moraga? And I get an answer, yes. But I hope you realize it's got to do a lot of reasoning, because it has to figure out that USA contains California, that California is actually the same as Golden State, that the Golden State contains Contra Costa, that Contra Costa contains Moraga. I can even make more difficult by saying, does Uncle Sam contain my town? Now basically you have to go through all the triples just to find that that relationship is true. Okay, that was the reasoner. I would say that I can take questions now. Sorry, yeah, okay.
So is it accurate to say that RDFS plus features and semantics are precisely the same as AlleGraph?
Well, it's a reduced subset of OWL. And people call it OWL-like, but there's also a formal OWL-like, but it's not the formal OWL-like. I mean, there's 3 forms of OWL. That's why I call it RDF++. But there's a number of people all working on the same subset.
Sorry, I didn't get your last sentence there.
So this,
people all working on what?
they're all working on this roughly the same set of predicates. And Jim Handler, a well-known person in this community, is actually working on a book where he actually will completely describe just this subset of RDF and OWL as a practical way to do reasoning over triple stores. And I hope he gets out with this book real soon, because that would make my life a lot easier. I can just point to that book. Excuse me, can you speak up a little bit?
Oh, sorry. Is RDFS++ a subset of what W3C has defined to be OWL-like?
Yeah. Yeah. More questions?
Could you show consistency checking?
We don't do consistency checking. If you want to do consistency checking on, say, an ontology that you build, then you have to apply Racer to your ontology.
Okay.
To make use of Racer, is Racer integrated by means of the dig interface?
Racer is also written in the same language as AllegroGraph. So if you want to, I mean, there is a dig interface, but for better performance, you can have AllegroGraph and Racer loaded in the same image, and then Racer will read the triples directly from the triple store. Does that make sense?
Yeah.
So you can do the stuff in the same memory image. But in the fall we will have a whole tutorial about how Racer can work with AllegroGraph, or works with AllegroGraph.
Great.
Okay.
Any other questions?
Well, perhaps you could recap in terms of what of all the stuff that we've seen this morning. Is it all fully available and fully documented in your current release product, or what's the status?
Yeah, the demo that you just saw, that whole file will be made available to people that send an email to Steve, and you can run that with the current version 2.1.
Thank you.
And you can run it both from Java or directly in Lisp. Oh, that's one of the things I didn't really show you.
I didn't understand your last statement. You can run it directly.
Well, if you want to, you can do the reasoner both. You can also run it straight from Java. The same things that I showed you in the interactive session work in Java.
Java. Okay.
Okay.
Okay. Well, thanks again for attending this seminar. We'll be having another...
This line is now muted.
Can you hear me?
All callers are muted.
We'll be having another seminar on Monday. Dean Alamang of Top Quadrant will be spending half of the time showing how Top-Rate Composer can be used as a ontology modeling tool working with AllegroGraph. I'll be sending out a survey, and we'll be posting a recording of this as soon as I can get it post-processed. I want to thank you all for attending, and again, don't hesitate to send us email, ask questions,